too, so that's good.
Perfect.
We can hear you too.
Perfect, thanks.
Okay.
All right, well, thank you all for your patience. Sorry, we were just trying to get a few things set up, and Darin was in very high demand, and so he was being kept in meetings. I was partially responsible for that. So it's a great pleasure to welcome Professor Darin Ragozzine from Brigham Young University. Darin and I go way back to the days when we were both postdoctoral fellows at the Harvard-Smithsonian Center for Astrophysics. And from there, he's bumped around to a couple places as faculty, but he's landed in Utah. I think he's staying there. And he's sort of one of the main lead astronomers in that department. And I believe he asks that if you have interested undergraduates who want to pursue astronomy or planetary science, please contact him.
Sure. Yes,
He's recruiting excellent students. Darin has worked on all manner of things related to dynamics, solar system bodies, exoplanets. He's been a real pioneer in that field. And today I think he's going to tell us more about outer solar system, small bodies. Darin has also asked that we try to keep this like a traditional informal tap colloquium. So if you have questions, please raise your hand to interrupt. And to those of you in Zoom land, we have speakers and microphones in here. So I do believe you can just chime in and interrupt and we will hear you. And if not, feel free to post something in the chat and we will try to follow up on that. And with that, I will let Darin take the mic.
Excellent. Thank you very much, Caitlin. I appreciate the opportunity to come to Arizona. This is my first time here on campus. It's been great. I've had some great meetings and I appreciate that. Today I'm going to be talking about measuring the shapes of outer solar system small bodies. This is work that I'm doing mostly in conjunction with a graduate student, Benjamin Proudfoot, my graduate student, and also an undergraduate, Dallin Spencer, who will be applying here to go to grad school. But then another former student, Seth, Simon Porter, Southwest Research Institute, helped with the integrator that we'll be talking about, and have some collaboration also with Will Grundy at Lowell Observatory. And so we're talking about the outer solar system and getting into those kinds of things. A little introduction about my exoplanet work before I get into that. I'll introduce the Trans-Neptunian region, kind of talk about what's going on there, get everybody up to speed on the current results, which assume Keplerian orbits, talk about how we might move to non-Keplerian orbits and modeling, and whether this is detectable or not, and kind of what the prospects are, and then give some specific examples, and then get into some future work. And again, you're welcome to ask questions at any time, and I'll kind of keep track of that. Before I get into the outer solar system work, I wanted to talk a little bit about my exoplanet research area, just to familiarize you with it. So I study dynamics of systems, especially, so I do a lot in exoplanets, but my main thrust is dynamics of systems of multiple transiting planets from Kepler. This is a plot of just the multiple transiting planet systems, orbital periods versus planet size. And you can see there's a large variety of systems here. So as a planetary dynamicist, when we discovered all these objects with Kepler, this is like now the largest population of objects that exhibit planetary-like dynamics, where you have one large body in the center and many small bodies orbiting it. And so we've been doing lots of great research there. The problem is that this is a very biased sample. And so we've been doing work with Matthias Hett and Eric Ford at Penn State on trying to understand what the true underlying population of planetary systems is like. And so generating a population of planetary systems, not just planets, but whole systems. And then checking, for example, that the period distribution matches the observed period distribution. And probably our most recent interesting result from that is that, and this has been suggested by others, but we think we did a pretty good job of demonstrating that a natural explanation for the multiplicity distribution, how many planets are seen, how many 5-planet systems, 4-planet systems, and so on. A natural explanation for that is that the eccentricity distributions and the inclination distributions of those systems decrease, they get flatter or colder as you get to higher multiples, which makes sense, right? This is actually generated from a model that produces stable systems sort of by construction. And so you expect stable systems to have lower eccentricities and lower inclinations. But it also is a very good match to the data. So that's been really nice.
Right, can we?
Yes, question.
Do you mean that the actual planets that have, the actual systems with many planets are colder, or that the ones that you observe with many planets
No,
are
the
colder?
actual systems are colder. Yes. There is a bias towards in colder systems, you see more
Right, yeah.
planets. That's been taken out. And this is the true actual inclination distribution. Now, there are many knobs to turn. So, this isn't, and you can see that we, this sort of smooth shape for these came from this construction of stable systems. And so, is this the exact right shape? I don't know. This orange line is an example of a previous sort of empirically motivated estimate of what this might look like. We find this with some range depending on which knots you turn. Yes, no.
Is there some sort of equipartition between the eccentricity and
Yes.
inclination? Is that built in or a?
That's built in. Yep. Yeah. So this uses the angular momentum deficit, and to keep eccentricities and inclinations low enough that the system would remain stable under certain conditions. And the angular momentum deficit is partitioned between the eccentricities and inclinations.
Andrew had his hand up.
Oh, yeah.
Yeah. Sorry, since I know you're covering a lot of ground, I'll just ask here. Is this recent work still consistent with the idea that the of sort of a bimodal multiplicity distribution is actually a true population of singles? That
was one of our results. Yeah, is that there's but that now we've come back. Okay, so there's this thing called the Kepler dichotomy, which has been. Basically, the story of the Kepler dichotomy is if you have a single, say, multiplicity and a single inclination, say all exoplanetary systems are 5 planets with 2 degrees mutual inclination. No matter how you change those 2 numbers, you can't explain the distribution of planets. You end up with way too many singles. So there's many different ways of solving that. This naturally solves it without invoking an additional new population. So this is now a single population model, but now with a correlation between inclination and multiplicity that solves this. But that doesn't have to be the answer. It could potentially be something else. So even though there are hundreds of systems, we still only can solve for maybe 10 parameters of the population model. So if you come up with another population model, maybe you could also match it. And Renu, did you?
I think I got the answer to my question. So there are 2 things going on here. You're doing synthetic models.
Yes.
You're generating random planetary systems,
Right.
And then somehow you're normalizing with the observed systems.
Yeah, so we run it through a simulator, a Kepler simulator, basically, and then compare many different observables: the period ratio distribution, the period distribution, the number of observed planets per system, the duration distribution, the ratio, so a lot of these different things, and then we only keep the models that match those. Yeah, so there's some interesting work. We feel like we've really been getting at and the fun thing about this, these are the underlying populations, these are the real populations of the planetary systems. And we're able to explain all the Kepler data pretty satisfactorily. So that's really good. So this is kind of a top-down approach, population modeling. The other thing that I'm working on, just got a grant to continue working on. Is starting with individual Kepler systems and modeling them in great detail. We're using a photodynamical model, which is a more advanced model than a TTV model that you may have heard of. That is to say, we have all the physical and orbital parameters of all the planets, including masses, and we generate a light curve, match that to Kepler, and then repeat that process and solve for the final distributions and get out, all the fancy statistics of corner plots. But we are starting to get things that haven't been observed before, like true 3-dimensional mutual inclinations between planets and systems. Densities of planets, densities of small planets that haven't been detected before. I have another graduate student, Daniel Jones, who's working on asking if you put a dynamical stability limit, what does that do? This plot is of particular interest here, which is showing that these red dots are showing these were the densities of these planets from a model that solved for the dynamical interactions between the planets. We actually have a measured density. This is showing what the stability limit would be. So for this planet here, if you add in dynamical stability as another constraint, it's just basic dynamical stability as another constraint, you actually constrain the density to be a third of what the actual perturbations measure. Part of that's because perturbations aren't very good. Part of that's because of dynamical stability hasn't been applied yet. But we're adding in some more of these pieces. But let's move on from exoplanets to the topic of the day, which is Trans-Neptunian objects, Kuiper Belt objects discovered in the outer solar system. This is an animation from Alex Parker showing the discovery as a function of time. And so when a dot shows up, it has been discovered. And larger dots for larger objects here. So Pluto was known for decades at first. All the orbits of the planets here, Jupiter, Saturn, Uranus, Neptune. And not very much of an orbit has happened, so you can't see very much, but you can see the inclinations. If you now take this and put an edge on, you can see that the planets are all very thin compared to the Kuiper Belt, which has this very dynamically excited component. Right, so there are about 2,000 known Kuiper Belt objects at present, and we want to understand them better. We recently sent a spacecraft to Pluto, and New Horizons took this picture, for example. This might be, if you were looking out the airplane over Pluto, what you would see. Nitrogen glaciers that are convecting and water ice mountains and haze in the atmosphere. All these great things, right? So we have this one case where we know a ton of information, but then, usually this is what we get. When it comes up here, usually this is what we get, right? A little moving dot. This little moving dot here, it's moving more slowly on on the screen here. But anyway, this little moving dot, all these other objects are stars. This little moving dot is from our observations. BYU recently joined the Astrophysical Research Consortium, so we now have access to the 3.5 meter telescope at Apache Point. These are some of the observations that we've taken of this object moving back and forth. This object is 1996 TC36 LEMPO. And so if you imagine pretending that you could zoom in on this object, so this is the arrow from before, right? Zooming way in on this object, right? And pretending that you could see things, that you might start to notice you might start to notice that actually this isn't a single object. This object has a moon. And actually, if you zoom way in on this inner object, then you can just barely, with the Hubble Space Telescope, resolve that there are actually two components in here, separated by less than 1/10 of an arc second. And this is the Hubble image on the right, a zoom in of this region. And so we have now the LEMPO system, 1999 TC36. This is the only, as far as I know, this is the only solar system trinary. Right? We have a lot of triples and quadruples and things like that where, well, not any quadruples that I can think of. We have a lot of asteroids with 2 moons, or Haumea with 2 moons, or Pluto with 5 moons. But this is the only case where we have sort of a hierarchical triple in the solar system. 2 objects near equal mass orbiting close to each other, and then a little moon going around on the outside. For 10 years, this system has been a challenge to me. I don't know if it's been a challenge to anyone else. But the original fit to the system that discovered that the inner object was itself a binary. They didn't do a full 3-body fit to this system. They just sort of estimated the interior orbit and the exterior orbit and left it at that. And if you know what these plots look like, you can see that they have huge errors, right? This is a very, very bad fit, but it was adequate to kind of get the idea of the system. And so there's been this challenge for 10 years of, can someone do a 3-body fit to the system? And we recently completed that in this paper in prep. So we now have a 3-point mass model for this system. We'll talk more about that a little bit later. But today, what I really want to focus on is not these higher order multiples, which are really interesting, and I also study, but just binaries, systems with 2 known components. So what have we got? We've got, of these 2,000 TNOs, about 100 of those are known to be binaries, and that's just a fraction of the ones that have, that's actually a large fraction of ones that have been observed. The binary frequency, the underlying binary frequency is probably 10, 20, 30% just for the ones that we can resolve, just for the ones that we can detect. And then probably many more that we can't see, as we'll talk about later. So binaries are very common in the outer solar system. About 40 of these have had multiple observations tracked enough where we know their orbits in detail, eccentricities, orbital angles, all those things. And then there are these 3 higher multiplicity systems, Haumea with its 2 moons, Lempo that I just showed you, and then Pluto with 5 moons. Pluto is kind of a hierarchical system because Pluto shares sort of an inner binary with four outer moons. Caitlin's done some work on that. So that's a very interesting thing. So I'm a big fan, well, as a dynamicist in general, but also just as someone trying to figure out planet formation in the solar system. I'm a big fan of these objects because these are the most information-rich Trans-Neptunian objects, right? These are, if we're going to learn things about densities and shapes and sizes, we're going to be looking at these objects, right? Just like we did for stars 100 years ago and things like that. So what have we got? I think actually I'll skip over this slide. This is kind of a slide just to point out that you can start by saying that there are 10 to the 160 calculations that you have to do in order to solve the motion of every particle in the universe. And you can reduce it down to a one-body problem if you make some assumptions. So in particular, the main assumptions that we use in orbital dynamics are to collapse the entire mass of the object to a single point, to use Newtonian physics, we don't need GR here, and to only work 2 objects at a time. Okay, so if you do that, then you end up with Keplerian orbits, orbits that are ellipses, that are fixed in time and space, fixed in space and orientation. And this is basically for binaries. Now, not Lempo or Haumea where there are multiple known components, but for these large number, 50 or so cases where there are just 2 known components, Keplerian orbit model is the only thing that's been tried up till now. Okay, so and one of the reasons for this is usually there's sort of 14 data points and sort of 7 parameters. There's not really a lot of data. There's not this wealth of data to do, but the data are extremely precise. So we'll come back to that. And so what we have found overall, what the community has found, mostly Will Grundy at Lowell Observatory, is that when you combine, even when you combine observations from different telescopes and different instruments, these have all been cross-calibrated to each other and checked and things like the center of the galaxy and things like that. So when you combine all these together, there doesn't seem to be any serious systematic errors, and all of these TNBs have pretty good fits with Keplerian orbits, nearly all of them. Okay, just kind of as a preview, I'll mention that our group has now refit everything with Keplerian models, and we agree that it works well, and our modeling technique compares well, gets the same answer as other methods. So I want to kind of start by motivating this question of, well, what do we learn? Okay, so we have these Trans-Neptunian binaries. What's the current phase of the field? And one of the most interesting things that's happened in the last couple of years is this plot. So I don't want you to worry about the colors very much, but what I want you to think about, this is a separation in terms of very close here near the center and further away here at the edge of the plot. And then the orientation along the axis here, along the azimuthal axis, I guess, is the orientation of that binary relative to the orbit of that object around the sun. Okay, so on the left here, less than 90 degrees, call these prograde. The binary orbit is in the same direction as the heliocentric orbit around the sun. And then on this side is retrograde, where our orbit is where the binary is orbiting the sun one way, but the binary components themselves are orbiting the other way, right? And so you can see that most things are prograde, but there are some retrograde things, and this is true in different colors and different regimes. And so this is a really nice piece of information that just came out sort of a couple of years ago. There were a variety of predictions for what this plot would look like 10, 15 years ago when people started thinking about formation mechanisms for Trans-Neptunian binaries. This one plot rules most of them out immediately, and instantly favors the streaming instability model. Now, Arizona PhD Rishin Lee and Andrew Uden worked with David Nesvorny at SWERI to perform calculations of the streaming instability. So this is a formation model where you have gas and dust, gas and particles in the system, and there's interactions between the gas and the gas and the particles and the particles and the gas. And you include all of those components, and you get this streaming instability, which naturally creates these clumps. And these clumps, due to the gas drag and the way the instability works, these clumps can naturally reach a point where they are gravitationally unstable and they collapse. Right? And so they reach a point where the density gets high enough that they collapse. And this is a very natural explanation. This is a very natural explanation for things like the meter size problem, where I have been telling students for years in planet formation class, and then magic happens and we get the planetesimals, right? So we can now maybe replace magic with the streaming instability, which might still be magical. But we have the streaming instability that does this. Now, the beautiful thing about the streaming instability model, we'll replay it because it looks pretty. Anyway, you can imagine that it's going again. The nice thing about it is that it makes a prediction. If you then take these clumps and imagine their gravitational collapse and model that, you would predict that you get 80% prograde and 20% retrograde Kuiper Belt binaries, which is exactly, almost too exactly, Andrew and I were talking about this, a little too exactly what you get from the observations. Now, these observations are a little bit biased, probably not in inclination, but in other ways they're biased, things like that. So I wouldn't say the story is done yet, but I would say that this is actually one of the strongest direct observational evidences for the streaming instability, which is a very popular model now for a wide variety of planet formation problems, not just the Kuiper Belt. And so this is a really nice connection directly between Kuiper Belt binaries and the streaming instability. And one reason this works really well is that the Kuiper Belt is a very primordial, very unperturbed population of systems. And so therefore has this opportunity to be to tell us a little bit more about the early solar system. Now, there are still questions about whether exactly this distribution is the exact output of the other distribution, but it's a really good sign, really nice piece of work that they've done. There's another piece of evidence for the streaming instability, which is the New Horizons mission that flew by Pluto that I showed you before, flew by another cold, classical, really primordial object in the solar system called Eris, and took this picture, which looks very much in picture, but then also geologically like two objects stuck together. And one thing that was interesting, we got this picture and it was only a couple of weeks later, we found out that actually it looks like two spheres in projection, but it's actually two flat objects that are touching. And they have done some geology about the neck region here where they're touching, and have found that they can't have hit each other very fast or wouldn't have kind of nicely centered together the way it is. So that doesn't leave a lot of options for how this object formed. You have two objects and the object is spinning around in the same way. So the story is you start with the streaming instability, you bring in a bunch of particles, and they all kind of collide, they coalesce and collapse. Within this rubble pile, you form independently the two pieces. They are flattened out because they're rotating, and then gas drag or some other process, maybe planetesimal interactions, bring them in and slowly bring them in until they just touch and become one object with the right rotational axis and all those kinds of things. So the authors of this mechanism invoke the streaming instability to start this process to explain how you get down to this kind of object. Okay, so the streaming instability model is one that is really now having some of these really interesting components that we're seeing in the outer solar system. And I think that
Question.
Oh, yes. Question.
In those simulations, these you start with this bunch of particles. Is it the two largest, the most massive ones that find each other, or is there any kind of bias like that?
So the simulations, so there's the streaming instability simulations that I showed. That's the gas and the pebbles. That gets you to the point where there's you reach the critical density. Then you switch to a whole nother simulation mode, like using PKD graph, for example, it's like a big n-body model. But it's the resolution's not not perfect, and there are some numerical things that still get to be improved, I think. And so I'm not sure if we could answer that question well, whether this happens. There is a general feel when they do those simulations, they do end up with most of the time, most of the mass being accreted into 2 objects, sometimes more, sometimes 3 or 4. But the status of the smallest pieces, which are basically single particles in this, only semi-resolved system, I would say is still could use some work. But the story is nice, and it's an actual way of forming these contact binaries. So as we continue to study the outer solar system to learn more about the streaming instability, there are other tests that you can imagine, right? Are the physical properties like the densities and the colors, do those make sense? The colors actually make a lot of sense, so that's good. How often do you have these contact binaries or unresolved binaries? So you can remember we just did LEMPO, and I talked about how HST was just barely able to see the difference between them. Well, if it hadn't, right, then we would have just thought that there was this one moon around this one object, and we wouldn't have seen that it's actually the LEMPO is sort of it's kind of like a pre-Arrokoff before these 2 objects merge. Now, to be fair, it's about 10 times bigger than this object, so they're on totally different size scales. But still, the idea here is that if we understand more about the frequency of binaries below our resolution limit, how many binaries are contact binaries, how are the spin vectors relative to the orbit vector of the body, right? This has a very specific prediction that there'll be low obliquities, low angles between the spins and the orbits, and things like that. So these kinds of questions are best done by doing additional studying of Trans-Neptunian binaries, particularly with non-Keplerian models, right? Because we can actually start to answer, we can actually look for binaries and spins and things like that. So unresolved binaries were really challenging. I'll show you a plot about that. Even if HST can't see them, James Webb will push things down by a factor of a couple, depending on the wavelength regime and things like that. But there's still a lot of space. These objects are very far away, so there's a lot of physical space for there to be unresolved binaries. Another real challenge is to get this orientations of the spin axes of these objects. That's basically not known for basically any Trans-Neptunian object except for Arrokoff and Pluto. Other than that, you're really on shaky ground because you can get the projected angle if you get the light curve and you know the shape, but you don't know the shape. Anyway, so you don't get very much information on these, but with non-Keplerian modeling, we can directly infer the spin direction. So that's really exciting. So let's talk a little bit about the physical parameters. What have we learned about the physical properties of Trans-Neptunian objects? And this plot to me is kind of an evidence of sort of the preliminary state of the field, which is these are all of the densities of all of the known Kuiper Belt objects. There's only about 20 on the whole list. Most of them have huge error bars. And there's really not a lot known about the density, which you think in terms of astrophysics and planetary science, it's like the #1 thing you want to measure, right? We don't have very much information about it. To kind of orient you on this plot, we have diameter in log on the x-axis here, density in CGS on the y-axis here. So to kind of orient yourself, this is like the size of the United States. This is like the size of Arizona, and this is like the size of Pima County, right? So that's kind of, we have a huge range of diameters here. And then in terms of densities, we have sort of the density of water ice, which is 0.92. Here, pure water ice, and the density of rock up here at 3, right? So, okay, so we have these objects. So we have Pluto, for example, sort of halfway between rock and ice, because we think Pluto is sort of half by mass rock and half by mass ice, something like that, right? That's our model. But I want to draw your attention to this object here, 55637 or 2002 UX25. It is larger than Arizona, right? So it's like 625 diameters, 625 kilometers in diameter, but less dense than water ice. Cosmochemically, probably all these objects have basically the same ice to rock ratio, right? You can see here, Eris seems to be an outlier, but that might be because it experienced a giant impact or something like that. But it's unlikely to try to create an object when there's lots of rock out there to end up with an object that's just pure ice, right? So the explanation for for this object, or for these objects down here, is porosity, right? Empty space in between the objects. But we have an object here that's 650 kilometers in diameter and needs a macro porosity, we call it, empty space on the inside of like 50%. Explain its density. It seems really unusual, and it will get worse later when I show you the non-Keplerian results for this object. These objects down here, this is fine. So we actually, for example, we find asteroids, which are known to be made of rock, which have bulk densities of 1 down at this size scale. That's fine. But as you start to creep up here, this isn't impossible. But for example, this object can never have melted, because you melt just a little bit and you fill in all the holes, right? So you can never ever melt, even though this object has a moon. So it's like it never got hot, but it had an impact anyway. So we'll come back to it. We'll come back. Let's talk about the TNO binary problem a little bit more specifically. You start with astrometric observations. So you take a picture, you measure the relative position between the two objects. This is an example of Boris and Pabu, a classical object and its moon. And what I'm showing you here, the dashed line is sort of an average orbit. In actuality, the orbits change slightly over time due to the viewing angle of the Earth changing and things like that. The circles are centered on the model data points, and inside, you can barely see them. Inside these circles, not exactly at the center, are these little tiny crosses. Those are the observations. The observations are 2-3 milli-arcsecond precision, very precise centers positions. As I mentioned before, all of the previous models assume Keplerian motion. And this is a great approximation most of the time, right? So you can see this is a pretty good thing. But some of the time, we already know that it fails. Eris, which is the most massive object in the outer solar system, beyond Neptune, that's known, has the Keplerian model fails at 6.3 sigma. Silesia, another model, fails at 3.7 sigma. And there are several 2.5 sigma failures, too many to be explained. So the Keplerian models can't quite be right. It's also possible that you have an adequate Keplerian fit, but then when you try the non-Keplerian fit, it's much better, statistically significantly better, or provides interesting upper limits on the non-Keplerian effects. For example, secret preliminary result, when we solve for Boris and Pabu's orbit, we actually get that it probably is an unresolved binary. So we'll come back to that. And this is with the current data. As James Webb gathers more data, as HST gathers more data, this will only get worse. Non-Keplerian effects grow in time, something like the baseline squared. And so you can imagine that it won't take very long. They'll all need a non-Keplerian model to be fit. Okay, so what are the dominant non-Keplerian effects? What are we going to try to include in our model to take our model to the next level? The natural thing to do, as I've already implied, is to relax the point mass assumption and allow these objects to have non-spherical shapes, right? And so what do? You take the gravitational potential and you expand it to higher order. Instead of just the 0th order term of the mass, we now include the dipole order and the quadrupole order. If you go to the right reference frame, you can remove the dipole order. However, you do have to make an assumption that the photocenter, that what you see is the center of light of the object, is also the center of mass of the object, which may not be true. We don't include a detailed dipole order, but we do allow for there to be a constant offset. That's the first time people have done that, so we want to include that effect. And then we go to quadrupole order. That's going to be sufficient for now. So here's what the expansion looks like. You take the potential and you expand it out. This is now in planetary science terms. You have the oblateness measured by something we call J2, and the prolateness measured by C22. And so oblateness measuring how bulge it is at the equator, and prolateness measuring different longitudes if they're bulged out. Okay, so that's one obvious one. There are other non-Keplerian effects. What do you think, audience members? Other non-Keplerian effects? What would you add in?
Outgassing.
Outgassing. Okay, so these objects are out at 40 AU. They are not observed to have any coma of any kind. They appear to be point masses, as far as I know. So, and if they were outgassing, I don't know if it would affect the orbits substantially. That's a good question.
You've seen a coma around Chiron.
Yes.
They're a lot further out.
These are a lot further out, but I do have centaurs in my list. You have to outgas a lot to affect the binary orbit. But it's worth checking. So okay, good.
Tidal effects.
Tidal effects. What tidal effects?
Yeah, that's a good one. I feel like that would mostly just be more shape, which would just then add to the gravitational potential argument.
Right. So yes. So for example, if one object raises a tidal bulge on the other object, and that also adds a non-Keplerian effect. For these objects that we're looking at, at this size scale of sort of 1,000 kilometers and less, we expect what I would call those dynamic tides, tidal bulges raised by the other objects are going to be way smaller than the permanent bulges because these objects are made out of rocks and they're small. So for example, Mercury has a way larger aspherical, a way larger permanent rock asymmetry than the tidal bulges that are raised on it by the sun, for example. Moon is the same. Mars is like right around the limit where you could have a little bit. So these objects are small enough that those dynamical tides are not important. And then tidal friction is way too slow to be seen in these observations. Good, other ones. I want you to be fully satisfied that we've covered every.
Other bodies?
Other bodies, right? If there's an unknown moon, right, for example, which I've already alluded to. The sun could potentially, they are orbiting the sun, right? The sun's like a really distant third body, but it's really massive, right? It's like 1 billion times more massive than the object. So that could be it. That's why I asked when you said which tidal effects, because the sun, basically its effect on the orbit is to add a tidal component to the orbit. So it turns out that we have looked at this. We've checked that the sun, for example, Neptune and things like that, those are not important, or maybe if they are important, they're not meaningful because like we already know the mass of the sun, so we're not going to learn anything new if we include the sun in this model. So that turns out not to be an issue. But if there are other known components, they need to go in. But there could be these other unknown components, right? So they could be contact binaries, or they could be unresolved binaries. And there's lots of room, as I mentioned before, there's lots of room for unresolved objects in these systems. And just to give you, we have Erikov as a great example here of basically, you could model this as a really oblate object. Okay, we'll talk about that in a second. But then we have many objects, tens of percent of objects that have really strong light curve variations, which is indicating that you have two objects eclipsing each other that could be contact binary or certainly elongated. We have occultation measurements of objects that look like close binaries. There's a lot of evidence that there's a lot of these unknown components. So what do you do when you have these unknown components? Well, it turns out the dominant influence, of course, because we did the spherical harmonic expansion, the dominant influence of these can be approximated as a quadrupole, right? So you have sort of an effective J2. And if you do the calculation, a particular calculation with certain assumptions, you can show that the effective J2 is basically the mass ratio, so the unknown component over the main component, times the distance to that unresolved component in primary radii squared, right? So it's like you add in, this new effective J2. And when you add that in, when you start to think about this, there's a lot of parameter space that's possible. So let me look at this plot for a second. On the x-axis here, this is now imagine a hypothetical unresolved binary. On the x-axis is the distance between the two components in primary radii. On the y-axis is the mass ratio, right? So the contact binaries like Erikov that are basically the same mass and touching each other will be in the upper left-hand corner here. And light curve effects can kind of get you information on this upper left-hand corner. If they're really close together and they're really similar in size, then you can detect that in the light curve. The resolution limit, it varies a lot from system to system, but roughly, 10, 20, 30 primary radii. Below that, HST would not have detected anything. And so there's this huge parameter space where all existing methods can't really tell you anything. These red lines are sort of approximate guesses of the sensitivity of looking for non-Keplerian effects through the binaries. And so when you see a red line, all of the space above that red line could be detected. So there's this huge parameter space that's empty that can't be probed by any other method. And so up in this upper right-hand corner, barely unresolved, near equal mass, two near equal mass objects separated by 30 primary radii. The effective J2 was 1,000. It's compared to the shape of these objects, which might have a J2 of 0.05 or 0.1. For very oblate objects. So you can have very strong non-Keplerian effects with these unseen companions. We got to keep going here. So what is the dominant observational effect that happens when you have non-Keplerian motion? You introduce precession into the system. And you can imagine that, see how well these points match the observations. You would not have to precess very much in order to detect this. But in order to do it, you would need a new way of calculating it. At the time that we started, there was no existing public integrator that could just take n quadrupoles and integrate them. So we developed that. We call it Spinney. I'm going to kind of zoom ahead through here. Spinney is really good. It makes pretty pictures. Okay, and then we use a method called multi-moon, which is built on top of Spinney. It's a Python binary data fitter. It fits this data. It uses MC, Markov chain Monte Carlo, to do the Bayesian parameter inference. And we've validated it by comparing it to published data, synthetic data, and all kinds of things like that. So we're feeling really good about Spinney and multi-moon. We've also made it we tried to make it really easy for undergraduates to use. And we get things out like trace plots and corner plots and all the things that we love from our Bayesian inference. That's not too important right now.
I ask something.
Yes.
In what you showed before, do you assume that all the orbits of all these extra components are coplanar?
Yes.
If they're not coplanar, the orbital, you'll have not only precession on the plane, but you'll have the angle of nodes is going to precess.
Great point. So Demetrios brings up that when you're solving for the oblateness and the prolateness, you have to also solve for the unknown spin pole direction. So that's hard in the sense that it adds 2 more free parameters, but it's amazing in the sense that now you can, if you detect the non-Keplerian motion, you can also figure out the J2 pole, and in all likelihood, that's the same as the rotation axis of the body. So yes, you can, any arbitrary orientation of the 2 spins, any arbitrary prolateness and oblateness of the 2 bodies, and in any arbitrary Keplerian orbit. Mass distribution can now be arbitrary as well. You can sometimes break the mass degeneracy when you include non-Keplerian effects. I'm going to skip this part here. Basically, it says that we think that we should be able to do it, and get into some results before I start running out of time. So let's start with Eris. I mentioned before that Eris is the famous dwarf planet that's more massive than Pluto. I mentioned before that we have already know that the Keplerian orbit is a really bad fit, 6 sigma bad fit, and that we have this is one of the systems where you have a lot of data. So you fit it with multi-moon, and what do you get, right? So when you allow both Eris and its moon to be arbitrary quadrupoles in arbitrary directions, the fit is still bad. Okay, for example, you get the Eris must be more elongated than Haumea here, right? So Eris has to be like really elongated. We have a light curve for Eris. We know we have an occultation for Eris. We know it's not that shape, right? So that's not good, right? Well, what's going on? But remember, that was an okay fit. It was an improvement to the fit. But remember, these quadrupole fits are approximations, and that they can approximate, for example, other objects. So what if we add a new moon, unknown moon? If you add an unknown moon and you fit the 3-point mass model, you actually get an excellent match to the data. Really nice story for the explanation. This is the only model so far that's out there that can explain the Eris data, is adding an interior moon. So that's really fun. So for example, here are the residual distributions for the best, 2 arbitrary quadrupoles in any direction model. And these are sort of, the center here would be 0 sigma off in longitude and latitude out here. So you can see that we have, 2 points past 3 sigma, a couple all at 2 sigma in this model, not very good. But then you switch the 3-point mass model and you get the distribution of data that you expect, reduce chi-squared of 0.9, all the good things, right? And so we think that we have discovered a new moon of Eris, an interior moon. This is very similar to the exoplanet TTV discovery method. Same idea. This work is being led by my undergraduate, Darin, who's been applying to Arizona. We actually are curious about what it would take to convince, I don't know, the IAU or somebody that we actually discovered a moon if we haven't taken a picture. Because as far as I can think of, this hasn't happened in solar system history since Neptune. So maybe Renew knows, I don't know.
Oh, I was gonna ask, wouldn't the light curve tell you something? You can test this model against the light curve.
The light curve, so you get an unresolved light curve. Actually, we have light curves that are resolved of just Eris. So, but our prediction for the size of this moon is that its brightness is relatively small compared to the brightness of Eris. And so I guess you could, so I guess we haven't tried to look for like the little teeny tiny perturbation to Eris's measured light curve for this object. That is potentially a way forward.
And this is what Renew is asking, but
Yeah.
like, instead of showing these as a scatter plot, I mean, then surely there's a prediction for what these deviations are in time. So you can see if.
Yeah, so yeah, if you,
And that you could make predictions for what they should be in the future.
yes. Yes, let me, let me get to that in a second, yeah. So if this is right, if there is a new moon, then all the interpretations, all the studies of the Eris system need to be reinterpreted. For example, Eris right now has the second highest albedo of any object in the solar system except for Enceladus. If you add in this extra moon as a darkening, as a component that's emitting some thermal radiation that you were previously assuming was attributable to Eris, then you can bring its albedo down. It's still really high, but not quite as extreme and things like that. So these are some fun things that we're looking at. Also, this moon is coplanar with the existing moon, so that automatically tells you that this system formed as sort of a disk and all the pieces that go with the formation of this system. So we think that that's interesting. But the obvious question is, why haven't we seen this moon before? So here's sort of an animation of what's going on. We have the outer moon in green here, Dysomia, the known moon. Here's the inner moon, our prediction for it. We have a prediction at any time that we can look and check. And why hasn't this been seen before? Well, Eris is not only the largest object in the solar system, it was discovered out at apoapse. It's at 100 AU. It's 2 or 3 times further than all the other known Trans-Neptunian binaries, or the vast majority of them. And so the same angular resolution of Hubble corresponds to an even larger physical distance. And so if I were to place a sort of a rough estimate of Hubble on top of this object, it's too close. It's too close to resolve this moon. It'd be like 4 pixels, which if you've done the PSF fitting for Hubble, that's tight, especially for something that's much fainter than Eris. So that's a problem. So then you want to ask all these other questions, like, is it dynamically stable? Does it make sense in the history of the system? We've done some dynamical stability tests, and it is in this regime that is very stable. You can kind of tell that by looking. It's pretty far away from Dysomia. There's plenty of room in here. You're out at sort of 10 Eris radii, no big deal, right? So this is a system that is very plausible and is a much better fit to the data than before. So we're excited to publish the first discovery or something, suggestion. We don't even know what to call it yet, of another moon of Eris. Perhaps James Webb will be able to get close enough to see it. It'll depend on some of those parameters. Okay, I wanted to introduce one more object before I go. Well, I wanted to talk a little bit about one more object. This is UX25. This is the 650-kilometer object that's sort of 1/4 ice, 1/4 rock, and half empty space, right? So when we do the Keplerian fit has been known to work well for some time, but now we can give an upper limit on the non-Keplerian effects on the shape of the object. We put an robust upper limit of about 5%. So how does gravity compact this object to a sphere with a less than 5% deviation without filling in the empty space? Right, because the same, these same objects that have this high macro porosity elsewhere in the solar system are all very non-spherical. And then this object has a moon that may have formed in a giant impact. That's the most likely possibility. Everything looks like it formed a giant impact. How do you form a giant impact moon without collapsing or crushing some of the empty space? We don't know. Where we're at right now is my sophomore class. We are doing non-Keplerian fits for all of them, for all of the TNOs, and just doing them all at the same time. They are then, looking and checking how the fits look and kind of talk about it and work together. And we plan on publishing maybe even a series of papers where we talk about what we've got. We've already got some unresolved binaries. We've solved for gong shape and spin and density. We've had some interesting follow-up targets, things like that. So we're excited to continue that into the future. We also want to apply this to Haumea with its 2 moons. This is the one I worked on for my PhD thesis, and then later I got new Hubble data that broke my PhD thesis. So this is where the objects are, and these are the 3 sigma ellipses of where I predicted them to be. They're way off. They're 10 sigma off. It's not very far in terms of pixels, but there's that. So we have recently debugged Spinney and are excited to see if we can solve Haumea now with the new model. So I'm going to go ahead and conclude and just kind of re-summarize. The TNOs are an important part of understanding planet formation, especially the streaming instability. The binaries are a particularly valuable way of looking at this. That we've developed a new method for looking for non-Keplerian effects, and that we're now solving for really interesting things. We're solving LIMPO, we're solving Eris. This is a secret. We're solving for things. We're looking for chaotic spins. We're finding impossible spheres and things like that. Thank you.
Let's see if there are questions for Darin. You can ask them directly here, and anyone online can ask them in the chat or on mute.
You choose.
Okay.
So when you were talking about non-Keplerian effects, my mind always goes to gravity beyond the article. That's what I do. And have you thought about constraining a Yukawa potential at 100 AU, the mass of the graviton?
Sorry, say again.
Have you thought about constraining a Yukawa potential, the mass of the graviton at 100 AU?
Yes.
It will do the same thing. The Yukawa term causes an effective quadruple, like if you do small deviations from there. And I don't think anybody has put a limit on the mass of the graviton up to 100 AU, which is probably going to be the strongest that exists.
Yeah, so if you're looking for now non-standard model or beyond Newtonian physics, what do you want to do? These objects are poor for that because if we knew a priori their mass distributions and things like that, and could then look for small deviations from that, that would be great. But any observation I get, I can explain with some unknown moon or a mountain or something like that, right? So there's no way I would believe any interpretation of these that didn't just involve Newtonian mechanics.
I'm not asking to believe it. I'm asking to put an upper limit.
Oh, an upper limit.
What? Because I don't believe that you're going to find the mass of the graviton, but
Yes.
but the current upper limits are not. The quantum wavelength for the graviton upper limit is not at 100 AU. So an order unity error there will give the best mass of the graviton known today. I mean, LIGO has some because of the dispersion of the electromagnetic waves, and I don't think, like the relative dispersion, I don't think it's as big as 100.
I have not thought about solving for the mass of the graviton with these data. So I think, okay. So in terms of precision solar system, looking beyond GR, for example, usually what's usually invoked is lunar laser ranging, right? Because we can measure the distance to the moon to a millimeter for like 50 years. So that's really precise. People have looked at, the other thing you can do is the heliocentric orbits of these objects as they go around. People have checked that for non-Keplerian effects, and I don't know what the limits are if they're particularly interesting. But it seems, so one thing that seems to me that people have not done is comets. They're very loosely bound to the sun. They go out to 100,000 AU or 10,000 AU. They do have some outgassing and other physics that affects their orbits, but if you had a good comet model that you believed, And then you added in, actually, I did see someone somewhere once say that maybe you could detect the density of dark matter in the solar system region or something with comets. So it's not at the limit of something that hasn't really been done too much because there's just too many alternative explanations. But but maybe there's an unexplored part of parameter space there that I don't know about. Yeah, that would be a fun problem. Okay.
There another question in the?
Would you be able to point or, send an email at some time for you said Spinney was open source?
Yes, well, we're trying to make sure that it works fully before we're ready to do it. We could share Spinney.
Yeah, I was just curious because
It's
undergrads working on it, and that sounds.
it's intended to be. It will be open source. I think is more. We have it on GitHub right now, but it's private. But we're open to sharing it. So yeah, just shoot me an email. We can, we're willing to share that, talk about what you would use it for. It's pretty specialized mostly for this problem, but there are some other things. Since we developed it, there are some other codes that may even be better for that kind of a problem. Not for KBO binary fitting, but for the general sort of spins and orbits problem. So that's something. Cool.
Darin, some
Yes.
years ago, Keith Knoll, I think, did a survey of KBOs with Hubble, and he concluded that up to something like 100% of KBOs were contact binaries or very close binaries. What's the status of that now?
Yeah, so the status is at HST resolution. Okay, so the most recent thing is you're familiar with the OSIS survey. They took all the cold classicals detected in the OSIS survey and looked at all of them with Hubble. Alex Parker's leading this program. It's called the Survey's Legacy of the Solar System, something like that. He's presented, there are no papers have come out yet, but he's presented some detailed modeling that's the best that you could believe. And there's all kinds of things that you have to account for, like binaries, equal mass binaries are twice as bright as single mass binaries, things like that. He's done the best job at this as anyone has done. And his answer is that for cold classicals, down to sort of the resolution limit of HST, which is sort of thousands of kilometers, the number of the binary fraction is like 15%. That's the number he's getting out. Now, if you extrapolate, you can.
15, I thought the previous result was 30. That's the number that usually floats around.
Was that Alex's number?
I thought that was from Knoll et al. But
yeah, so that's the zeroth order answer.
Yeah,
So I would say a more sophisticated analysis that includes things like binary, binaries are brighter than faint objects, and a little bit better at what I would say. Keith never did a really superb modeling effort. I think he would agree with that. And so it turns out to be less than you expect because of something I can't remember. Something about the details when you look at it, like, oh, this happened. So that's 50%. So if you extrapolate, like if you take the binary frequency per semi-major axis, semi-major axis distance and extrapolate down, you can easily get to 100%. Most people think that's 100%. I think it's probably close to 100%. There's a lot of contact binaries that there's some estimates out there now that the contact binary fraction, not this one, is also 30%. So 30% here, 30% there. You add in a few in the middle, and they could all be binaries. I think that was Keith's point. They could basically all be binaries in the cold classicals. The hot classicals.
Size dependent. Did I understand that?
There's not enough. No one's done. There's either not enough data to answer that, or no one's really done it well enough that I would believe an answer. I think that's. But this new for cold classicals, this new survey should be able to answer a lot of those questions better than anyone ever has for the that's coming out of this. We agree.
And then I guess what recently New Horizons, right, detected or claimed a detection of two more, not contact, but sort of very tight binaries over and over. Tighter than obviously Hubble could detect.
Yeah, so they like to say that New Horizons, its 10-meter telescope is the largest telescope in the Kuiper Belt, which is true. So they can resolve things that Hubble can't. They have to detect them first. It's really hard, but they can resolve. So they can get super, resolution limits higher than Hubble and have found things in this intermediate regime. Yeah, and with just really sparse data. So there's a lot of evidence that many of them, most of them are findings, and we're excited to provide a really nice complementary piece with this analysis as well.
So I guess since Eris is bigger than Pluto, are you going to propose a mission to Eris to confirm your prediction of the moon?
Well, no. I was on a proposal for a mission to Haumea. That I think Eris is too far. It's like no one will fund it. But I guess the planetary decadal will come out eventually. What the plan is, or what people think the plan should be, or something. Yeah, good question.
All right, well, if anyone has further questions, you can ask
Yeah.
Aaron afterwards. Let's thank him for a great talk.
Thank you.
Ask him. I don't keep. But we can look it up. or-
No, I just wondered.
Yes.
Yeah.
Just check your,